All right, let's continue. Any questions? So I want to now focus on radial equation. Our radial equation, I want to copy here. Now we'll have to do a set of procedures. There's like some well-defined, do this, next line, do this, next line, do this, and then it delivers, right? Yeah, and so that's what we are going to do. So let's first start with changing the variable. So let we introduce r of r. Rather than r, we want to write this in terms of like u of r. So there's like a common question, why do we do this? We are going to do many things. Also tomorrow, the reason is it works, right? People studied this, they probably tried u over r squared, maybe they tried u times r. The one that works is this, and now we are only doing the one that works. If you have doubts, right, the field is yours. Be my guest, try anything you want and see what happens. So if I do this, so I need to calculate dr, d little r is going to be equal to 1 over r du dr, I acted on here, or minus u over r squared. Then I have this r squared dr over dr is going to be r du dr minus u. And I need to take one more derivative, this thing, d dr is equal to derivative of this is du dr plus r d square u dr squared minus du dr. Cancel this, and at the end we have r d squared u dr squared. And substitute it here. So I have this equation. So I have this piece calculated. It is, let me also rewrite this. So this is r, r, r. So this thing is, let me just rewrite. So this is r is equal to r. Now I calculated this thing, so I can erase this and write it this thing. So this r is u over r, and this r is u over r. So let me also, okay, let me do it in 2 steps so that we can keep track. So cancel this, cancel that. This is, oh, actually I can cancel, so this r and this r cancels. So this r cancel, and this is r squared. And I want to multiply this with minus h bar squared over 2m. So this is plus, and this piece is minus h bar squared over 2m. Let me write r squared here. Yes.
Where did r squared come from before
So this r squared, this one. So this one we obtained in the previous, right? We said let's separate. When we separated, right, we had r squared here, and this r squared. Yes, we multiplied, right? There is like r squared here. We multiplied. We said divide by y times r and multiply by minus 2m over h bar squared r squared. I actually forget it first and then I put it later. If you don't put it, you cannot separate. Okay, so this is that. So let me just write this cleanly. Minus h bar squared over 2m d squared u d r squared plus so I will write E on the other side, so it's going to be like a Schrödinger equation. So V plus h bar squared over 2m r squared L plus 1, close this parenthesis, U is equal to E times U. Somehow I didn't miss anything. It looks like correct. Oops. So this is the equation we are going to work. So this, you can see this piece. This one is, I can define this to be like an V effective of R. So the effective potential has usual interaction V, which is given to us, but also you can see there's like this 1 over R squared term, which is positive, right? So this is going to be positive, and it is going to be like, so this piece is going to be centrifugal term. It's going to like push the particle out of the center. And the normalization, let's also write normalization with this new u variable. So this is dr r squared is coming from the three-dimensional volume integral, and we have r squared. When we redefine it, we have dr r squared. We defined r to be u over r. So this is going to be u squared over r squared. Cancel this. Then our normalization is from 0 to infinity. dr u squared should be 1. That's what we chose, right? That's also convenient. It's like normalization in 1D, but the limits in 1D was like from minus infinity to plus infinity. Here is from 0 to infinity. Good. And now we have to specify V and solve it and see what it looks like. And that's what I want to spend some time with. So let's consider an example. So, example. Let's consider infinite spherical valve. That's the simplest thing we can do. And in the infinite spherical valve, the potential is a function of r, and it is 0 if r is less than some radius, infinity otherwise. Right? So let's try to solve this. So here's my coordinate system. Yes. So this is my V. So there is some point A. Inside V is equal to 0. Outside V is equal to infinity. And this is R. And let's first focus on L is equal to 0. Now, after that, I also consider L is non-zero. Then the equation is here. Let's copy. So this horrible looking equation. So first, we took L is equal to 0. Let's get rid of this. And inside here, this is going to be 0, right? We can also get rid of this. So that's the solution. That's the equation we need to solve. This side. In this side, I don't need to solve anything. I just need U to be, what is U outside in an infinite potential? 0, right? Nothing can be in an infinite potential. And this thing is, right, simpler than anything else, right? It is like, let's do this. So this is minus 2m over h bar squared. And this is some, also obviously we require E to be bigger than 0, otherwise we don't have sensible solutions. So this is going to be some k squared. Then the solution is U of r is A sine kr plus B cosine kr. Exactly like in 1D, there is no change. But now the boundary condition we need to think is U of r at is equal to 0 should be determined by r of r at 0. And this is U of r divided by r at r is equal to 0. And if I take the cosine term, this is going to blow up, right? Because cosine at 0 is 1. 1 over 0 is blowing up. So I'll just take this to be 0. Then the solution is only this. And that solution, there is also second boundary condition. U of r is equal to a should be 0 because particle cannot be there. Then we have k times a is equal to n times pi, or k is equal to n pi over a. And this means our energies are E is equal to minus not minus h bar squared over 2m k squared, and k squared is n squared pi squared over a squared. Okay, so this one is also important. Let me box that in. So that's for L is equal to 1, right? Now let's, sorry, L is equal to 0, thank you. Now let's consider L non-zero, and things, yes.
K is complex.
No, K is real, right? So E is positive, like, so this thing is K, right? I call this one K, so that, right, if you take derivative sign is cosine, and one more derivative is minus, and it solves the equation. So this E is positive, K is real.
I thought you mean minus.
No, E is positive, right? I misspoke. I think if E is negative, if your energy is below the minimum of the potential, you don't have sensible solutions. Yes.
In this case, then En in this case, energy levels for L is equal to 0 is going to be this term, but we cannot give, for example, E2 is not, how can we?
So N is exactly like, there's no difference. N is as before. N can be 1, 2, 3, dot, 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 and solutions are as before, right? So you can have this sign solution, or you can have this solution, and so on.
Minus 1 also.
Minus 1? What do you mean?
N is equal to Because it's n squared.
If n is minus 1, like this,
No, for example, in E, we can do n minus 1, right?
but here we are like considering this like this. The boundary condition says k times a is some integer times pi, right?
Yes, oh, minus 1 also satisfies that equation. Is it degenerate?
What is problem with minus 1?
Constant x olursa. Evet, constant.
Oh, like this, right? Yes. Yes. Now I remember. Yes. Thank you. So you can also put negatives, right? But yes, okay. I think yes. Thank you. Sine of minus x is sine of x, right? If it is minus, right, it is solution times an overall constant, which is minus 1. It is not a linearly independent solution. It is exactly the solution with n 1, 2, 3, right? But multiplied with overall constant, which is minus 1. So it's the same, right? It is not, we are looking at linearly independent solutions. And so this solution, let's, for example, consider n is equal to minus 1. Your solution is sine minus pi over a times x. This is minus sine pi over a times x. But we need linearly independent solutions, right? If this is psi 1 and this is psi 2, we want psi 1, psi 2 to be 0. In this case, they are not, right?
Isn't it the definition of, isn't
No, this is not the definition. For degeneracy, you need to have this condition satisfied, right? They need to be linearly independent solutions, but their energy should be equal. Here they have the same energy, but they are not linearly independent.
okay.
Good. Yeah, good point. Thank you also. Okay, this was the simple one. Now let's do the difficult one. And the difficult one is going to require us to think about this L. So let's take this. So this is the solution. This is the differential equation. So V is equal to 0. So let me erase that. And how did I do that? Yeah, I can also rearrange things, but the problem with this is when you have this r square here, right, things are not simple sines and cosines, but they are kind of like sines and cosines. Let me write the solutions, and then I will try to convince you. Like the solution here is u of r is equal to some a r, so this j L of kr plus r little n L of kr. So this is the solution that satisfies this differential equation, and this little j and little n are kind of like sines and cosines, but a little bit more complicated. So this one is spherical Bessel function, and this one is spherical Neumann function. And let me list a couple of J L is given by this minus x to the L.
Would we be expected to write this?
No, right? So suppose in research you are exposed to something like this. Typically you put this in Mathematica, and Mathematica immediately gives you this result. In the old days you used to go, there was like some mathematical books. You try to look all equations one by one and try to find the one that matches your equation. It gives you the solution, and then you go and find Bessel functions. You look at the tables and you write this. You never derive. Of course, if you are a mathematician, you can derive it, but physicists didn't do that. But today, Mathematica solves all of these, and I'll show you how it does in a little bit. So this is 1 over x dx to power L sine x over x, and this one blows up at the origin, so we can forget about this spherical Newman function. It's not normalizable. And a couple of these, let's just write to at least see them once in your life. So j0 of x is sine x over x. So j1 of x is sine x over x squared minus cosine x over x, and so on. So let's also see how Mathematica handles this. So there is something called, okay, if you look at documentation you can find this, I think spherical, yes, it's here, spherical Basel J, and it is asking for two things. One is which order, right? So there is like L here. I'll use N. Let me use N. It's harder to write curly L in Mathematica, and X. And let's try to plot a couple of these. Plot spherical this. X 0 to, I don't know, 10, and I need to say something for N. For example, this is 0. So this is sine x over x, this one. So let's do like table. I can put this thing in a table and plot a couple of these. Let's plot N 0 to, I don't know, 5. Something like that. I need to, I think, put and let me also put the labels. Right, so the blue one here, okay, also I need to do plot range all. So the blue one is this sine x over x, yellow one is the next one, right? It's harder to track, and then the green one, and you can see they have zeros, and the zeros you match in such a way that you feed it into your boundary condition here. So let's also try to see how to manage the boundary condition. So the boundary condition, now it's a little bit more complicated, right? A times this J L K times A should be 0. And we need to find a way to determine the zeros of the Basel function. So need zeros of actually spherical Basel function. So that we can determine our energies, right? Unfortunately, Mathematica, I couldn't find zeros of spherical Basel function, but they have the zeros of normal Basel function. And normal Basel function is enough to determine spherical Basel function. There's like a relation like this. So Jm of x is equal to something like pi over 2x. I think I found this in Wikipedia. So this is uppercase is normal Basel function and plus a half x, and this is normal Basel function, and Mathematica has like a built-in for zeros of normal Basel function. Let me show you. So I think how did I do it? Basel J 0. For example, you can look at zeroth Basel functions. I don't know, first 0, and this will give you the expression, but you need to evaluate it, and it is at 2.4. If you go and put this number to Bessel function, it's going to be 0. And you can see zeros of normal Bessel function with integer shift is zeros of spherical Bessel function. So what we need to do is like we need to put 1/2 here. And this one you can see the first one is pi, right? J0 we determined here. When L is equal to 0, we already solved it here. It was like pi, 0 pi, 1 pi, 2 pi, 3 pi. Let's look if that's the case. This is the first 0. This is the second 0. I can also do the following. Divide by pi and numerically evaluate. This is 2 pi. And the third 0 is 3 pi and so on. And let's say
Ben yazdığınız kodlar
So now, so I want to do the following. Suppose the 0 of Bessel function is some beta and 0 and Lth Bessel function, right? I can determine this beta and L from my Mathematica, and this is what it is, and it is going to be equal to k times A. Then my k is going to be this beta and L over A, and if my k is this, my energy is going to be E is equal to h bar squared over 2m square of this. So this is squared and squared. And let me, so this one is nth 0 of Lth Bessel function, and this one is energy. And this one I just use exactly what I use, as if it is sine and cosine, right? With the sine and cosine we did that. So what I want to do is I want to look at the energies, show you the spectrum, and then finish it there. Yes?
You didn't write pi because it's supposed to include pi.
Yes. Everything is like, in the case of sine, it was like n pi, right? N pi is 0 of the sine function, and beta is 0 of the Bessel function. Right? A little bit complication we need to keep in our mind. And let's do a couple, and then I will plot them in like pictures so that you can see. For example, let's see. So this is 0. Okay, let's do the following. Let's calculate. I think I wanted to do the following, like table. And I don't know, let's say I want to calculate how many zeros. Let me just call it. If I do it n, it is going to mix up with built-in n, so I need to choose another number. I'll choose n, 0 or 1 to, I don't know, 5. And let's say, so this is n. So this is going to give me first 5 zeros of 0th Bessel function, which should be pi, 2 pi, 3 pi, right? And since I'm dividing by pi, I should have like 1, 2, 3, 4, and so on. So that's what it is. Now I know this is what I wanted. I can do it for more complicated case. I just copy. So this is L is equal to 0. This is, for example, L is equal to 1. You can see these are a little bit more complicated numbers. I don't know what is happening here. So this is 2, something like that. And what I did is like, okay, I want to, because these numbers, they don't make sense, I want to draw a picture and look at it, right? So for that, I define something like this. Let me first put this beta in a function so that I don't have to call this Bessel 0, blah, blah. So it is input is L, and its end 0 should be this thing. Basal 0. Right, now this function I need to put here L. I don't know if you enjoy this. In the old days I think it wasn't as much fun. You can play with Mathematica and get what you want, so you don't have to write equations and go to like Abramovitz and Stegun, right? There's like this 1,000-page book we had to go through. So let me define a way to plot this. I want to define this. This is not important. Let me do it and then I'll use it. You'll see the result. So this is and this is so I want to draw something, comma, something, and it is 0, 0, 15, 0. So this is just to make it look nice. It's going to go and put this line wherever my energy is. Now I can make a table of energies. Energies, I made a table. And in my table I have this L, Basel function L, and the beta of end 0. But since energy is beta squared, I need to take the square of this thing. This is the square. And I actually also want to put this here, otherwise Mathematica does not want to calculate, which is not very important for you. So this is n. Let's not go crazy. First 3 zeros of first 5 Basel functions. So these should be all numbers. Good. And right, these numbers do not make sense. Now I want to plot this. Let's plot and energies. And for the energies, I use this thing I defined, plot markers, H marker, and I wanted to make it a little bit bigger here. So that's the result. Let me take this. Okay, we had to write a little bit code for 10 minutes, but we didn't have to go to the library, right? And Mathematica is free for if you are O2 student. And you have like a nice picture. And let me explain what this picture is. So this one is L is equal to 0. This is L is equal to 1. This is L is equal to 2, 3, and 4, 5. So this is L. And this one is energy. For example, L is equal to 0 is the ground state. I don't know its value. I don't know. You can go and look at your table. It is like what? 9.8, whatever that means. And if you look at that, so this is smaller than any other energy. Next energy level is L is equal to 1, and it's just a little bit shifted, right? It's also non-degenerate at this level, but I'll tell you about degeneracy in a little bit. The next level is L is equal to 2, and then next level is you go the second 0 of L is equal to 0. So this is the second 0. You go one more. The next energy is third 0 of first Basel function, right? This blue line. You go again. This is now, here is, yes, what's that?
Before it, third 0, I think there's...
Yes, so this blue is, right, zeroth Bessel function. This is, if you look at this is going to be pi squared, 2 pi squared, 3 pi squared, 4 pi squared. Yellow one is first Bessel function, but they are not nicely written. First zero, second zero, third zero, and then second, and then so on, right? Hopefully that's what we call. So this is energy, and this is what we call energy level diagram, and it gives us the spectrum in a pictorial way. So these are energies, but now we need to think about degeneracy. And after explaining that, I don't know what this weird thing is happening. I'll finish it there. So, yes?
These energies wouldn't gain on the same level.
Yes, they are at the moment, right? This is why I draw this red line. None of them seem to be in the same level, right? These are all different levels. If you want, this blue is different, orange is different, and they are non-degenerate. I didn't look all of them. I looked first 10 and I couldn't find any degeneracy. If you go really high, there will be so many levels. At some point, things may be very close, but I don't know about that. Good. But this is the solution of radial equation. For the full degeneracy, we also need to think about angular part of the solution. And let me write that and I'll finish it there. So full solution, psi, is a function of r, theta, and phi. And we found the radial part. And radial part up to normalization is this Bessel function, this beta n L r over a. So this is what we found. And there's also this y L m theta phi part. Right? You can see for each L, we have like a different energy level. So there is no L degeneracy, but for each M, right? There is no M in the energy. So no M dependence in energy. And for each L, how many different M's do I have? From high school counting. How many different M's? Right? For if L is equal to 0, M is equal to 0. If L is equal to 1, M minus, right? M, exactly. M can go minus L to L, which is going to be 2L plus 1. And that means each level is 2L plus 1 degenerate. And that means this blue line is non-degenerate. This yellow line is non-degenerate. Green line is non-degenerate. For example, this one is threefold degenerate. This one is threefold degenerate. This one is threefold degenerate. This one is fivefold degenerate. Good. So let me give you an exercise. If I have the motivation, I can solve it next time. I actually solved it here, but we don't have time. You can use exactly the same script to solve. So here's your exercise. Consider, right now we considered infinite valve. Potential outside the valve is infinite. Let's consider finite valve. And what this means is V of R. Let's take minus V0 with this V0 some positive constant. If R is inside some A and 0 otherwise. And the picture is something like that. You have, so this is V of R. So this one is minus V0. So this is A. So this is R. And we want to see if there is, the problem is asking if there is any bound state. So this is your E. And so that means we need to look at only L is equal to 0 is fine. So by taking L is equal to 0, show that
But then why would you say just taking as
Because I want to see if there is only one bound state, right? So this is the bound state energy. You can also look at non-bound states, but that's the interesting one, and I will tell you why it's interesting.
Hocam nonetheless when we take L to be higher numbers, but the chance that there is going to be bound states is lower?
Yes, yes, because bound states are generally lower part of the spectrum, right?
Yes.
They have like lower energy, and if the minimum possible energy,
That
you
is just the most logical.
yes, exactly. If the minimum possible energy is not a bound state, you will say there is no bound state, right? Yeah. So by taking L is equal to 0, show that no bound state. If I found the condition here, let me write it. If V0 a squared is less than h bar squared pi squared over 8m, and you need to compare with 1D finite well. And does anybody remember the result in 1D finite well? What was the condition for at least one bound state to exist?
Always exists.
Right? There is always a bound state in 1D, no matter what V0 is. Even if V0 is infinitely shallow, there is a bound state in 1D. But if you do the same calculation in 3D, that's not the case. You need to have a certain threshold of depth of the well, otherwise your potential does not support any bound states. So try to work this exactly the same Bezier functions, and actually it's not even Bezier function, right? Because L is equal to 0 is going to be sines and cosines, and you are going to find like a transcendental equation, and you are going to find it has no solutions.
John, in the example, we don't need to use actual spherical coordinates, right?
You don't need to use?
Spherical coordinates.
No, there is you only need to solve radial equation, and radial equation is given here, right? Because we already took care of angular part. Just take this part, put L is equal to 0, and V is equal to minus V0 inside the well, and V is equal to 0 outside the well. There's like an inside solution and outside solution. Outside solution should be exponentially decaying, and you match, and then you find what your energy is. Any questions? If not, I'll finish it there. Thank you.